Have you ever really thought about how the code a chip designer writes, something that's totally abstract, turns into the actual physical silicon chip that powers your phone or your computer? Well, today, we're going to pull back the curtain and dive into the magic that makes it all happen: logic synthesis.
This is the big question at the heart of all modern electronics, right? How in the world do you take a bunch of text in a file and transform it into a real, tangible microchip with literally billions of transistors working together? The answer, it turns out, is a pretty brilliant automated process.
And yeah, that process is called logic synthesis. The best way to think about it is like it's the master architect of chip design. It's that absolutely essential step that translates a designer's big idea into a super detailed, buildable blueprint for the silicon factory.
So, let's get a little more formal. What is it? Logic synthesis is the automated process that takes a high-level design, what we call RTL, or Register Transfer Level Code, and turns it into something called a gate-level netlist. So think of it like this. The RTL code is what the designer writes. It describes the behavior of the circuit. The netlist is the output. It's a hyper-detailed map of all the basic logic gates, ands, ors, nots, and exactly how they're all wired together.
Now, this whole transformation needs three key things from the designer. First, you've got the RTL code. That's the design itself. Second, a set of design constraints. These are the rules. Things like, hey, this chip has to run at 3 gigahertz. And third, you need a standard cell library, which is basically the parts list of available logic gates from a specific factory. The synthesis tool takes all that, does its thing, and spits out that final blueprint.
So, why do we lean so heavily on this automation? Why not just draw the circuits by hand like they did in the old days? Well, the simple answer is that as we went from chips with a few thousand transistors to the billions we have today, doing it by hand just became impossible. The difference is truly night and day.
And this slide really nails that difference. Designing manually was just painfully slow and absolutely full of human error. One tiny mistake could set you back weeks. And on top of that, your design was completely stuck to one specific manufacturing technology. But with logic synthesis, the process is unbelievably fast, it's automatically optimized, and, get this, the same RTL code can be resynthesized for a totally new technology. That makes your designs reusable and portable, which is a huge deal.
So yeah, the main point here is that automation is a complete game changer. It slashes the number of bugs, it lets a single engineer design circuits that would have needed massive teams back in the day, and it allows for that all-important reusability. This huge leap in productivity is what makes things like yearly smartphone upgrades and the crazy powerful GPUs for AI even possible. And maybe most importantly, these tools can perform optimizations across millions of gates that no human brain could ever hope to do by hand.
Here is a perfect example of that power in action. A designer might write what looks like a really complex block of code, maybe with a bunch of nested if-else statements. For a person to simplify that, you'd have to draw a truth table or a Carnot map. It's a whole process. But the synthesis tool, it analyzes it in a fraction of a second and just goes, oh, wait, all this complicated stuff is really just a single, simple OR gate. That's the kind of intelligence we're talking about here.
But synthesis isn't just about making the logic work. It's a really complex optimization puzzle. The tool is constantly trying to balance this triangle of competing goals, all based on what the designer told it to do. Do you want the smallest possible chip to save money? Or do you need the fastest possible chip for a supercomputer? Or maybe the one that sips the least amount of power for a smartwatch battery? You can't have it all, and the synthesis tool is what navigates those trade-offs.
Okay, so we've covered the what and the why. So now let's take a look at the actual workflow. How does the tool actually go from that initial code to the final blueprint?
It pretty much happens in a few key stages. First, the tool reads all the code and elaborates it, which just means it builds an internal generic model of the logic. Then, it applies those constraints, all the rules about speed, area, and power. The third step is really where the magic happens: optimize and map. Here, it intelligently reworks that generic logic and maps it to the real physical gates available in that specific technology's library. And finally, it exports the finished plan, that netlist, for the MEX team in the process to actually start building the physical chip. So look, if you take away just one thing today, let it be this: logic synthesis isn't just some tool. It is the absolutely essential bridge that connects the creative, abstract world of code to the concrete, physical reality of silicon hardware. It's the translator that truly makes all of modern electronics possible. And that kind of leaves us with a final thought, right? We're always demanding more from our tech. Faster, smaller, smarter. So as these chips get even more mind-bogglingly complex, what do you think the next great leap in design automation is going to be? Is it going to be AI-driven synthesis, something else we haven't even thought of? It's a pretty fascinating question for the future of engineering. Thanks for joining me.